Please stop.
Good afternoon. We're coming to you live from the Ariel Dynamics Research Lab in Corona de Casa, California. My name is Bob Wainwright, and I am a colleague of Dr. Gideon Ariel to my right, who invented this system many years ago. And we're here today to present the newest version of APAS, which we call APAS Artificial Intelligence, or APAS-AI. This version of APAS took many months to create, but we now have a working prototype program that we'll demonstrate today and how easy it is to do a complete project from A to Z. Now, the first thing you want to know about the APAS program, if you have not used it before, you're not familiar with biomechanic kinematic analysis, is that it's composed of several modules. The most important module is what we call display. And display is where we view the final product and we ask questions about the performance. So in this case, we will show you a young dancer that we did a project from A to Z just 2 days ago. And I will bring up the file. Make it larger so we can see it. And this is the final 3D product of that dance maneuver. Play it for you. Now, in addition to that, we want to see the actual video of the dancer completely digitized. And we'll open another one. And we'll open the third one. And in order to see all the windows at once, we'll go Window, Tile. Now what you're looking at is the 3 actual videos and the digitized 3D stick figure. Play, and we see everything together. And we know this is a 3D creation because we can spin it around to another direction and prove that it is definitely 3D. In addition to the stick figure and the pretty pictures, we now want to add some data, ask questions about that performance. So I come up to the 3D and it asks me which file do I want. I want the same file. And it puts it down here in the data box. I say new 3D. And now we can look at the complete variation of questions we can ask. We can designate something in a linear space, segment angle, joint angle, length, and segment linear. And we can see it in quantity as a raw position, displacement, velocity, acceleration. And we have the option of doing any of the joints that we've digitized for this particular performance, including 3D, center of gravity, and we can look at it in the X, the Y, the Z, or the 3D. So for a very quick demonstration, we'll say linear displacement of the CG and the right foot and the left foot and the right hand and the left hand. And I'll select the Y so we can see how those body parts go up and down in the demonstration. So select. Now I've got the data here. I go up to the graphing module, say OK, graph, data, OK. Now we see the graph of each of those angles throughout the entire presentation. And again, we'll go Windows, Tile, so we can view everything together. Now it becomes very interesting because I can stop anywhere along the way, like in this particular point here, and immediately see what the values are for the particular body parts that we've selected. And now we'll begin to talk about how we get from A to Z for a completed project. The process begins by setting up 1 to 3 to more cameras, if you like, in a field where we're going to be doing the demonstration or the data pickup for the project. In this case, we're in the courtyard of the Ariel Dynamics Research Lab, and you can see we're looking at a calibration cube that has 8 points on it from 3 different camera views. We have found that if you're going to be doing a rotational event like dance or discus or shot, it's best to have at least 3 cameras, and those cameras can be arranged in a equilateral triangle fashion. If we're doing a more linear event like golf or gate, we can use 3 cameras again, but set them up more to the front of the actual event. The data capture starts in the module called CapTV. In CapTV, if we have cameras attached, which we do not for this demonstration, we'll click on the camera icon and set up the name of the file, the length of time we're going to be shooting, and the cameras we want to see it. But in this case, we'll just open up a prior file. That we call Megan second turn, open, and we'll do one camera, and we would do all 3 cameras to show you the demonstration of capturing the data. Once the videos are captured, they're saved to a file. Now that we have the videos, we want to start the digitizing process. In the past, we would have to do this indoors with markers or light markers, or outdoors by hand, frame by frame, joint by joint. Very arduous and long process. Now that we have the Digi-AI, we'll demonstrate to you how quickly this can be done to finish your project in a very short period of time. First step is to open the module called Digi-AI. And we first will deselect separate fields and reverse field. This was an old style of video that we would use, but now we're using progressive videos where every single frame is a separate entity in itself, so we don't need to separate fields. And we'll select the first video. The video that we're demonstrating is called Megan Second Turn. And here you see we have 3 already trimmed videos and 3 calibration videos. So choose number 1. And we come to the bottom, say Start Processing. And frame by frame, you can see that the AI program is automatically finding the joint centers and digitizing each segment of the move. When we finish, it says, do you want to process another video? And we say yes, because we have 3. Go up and select the second video. Start processing again from a different viewpoint. And for the third time, we'll say yes. And pick up the very last video. Start processing. And we'll stop it because we don't need to finish it. And we'll say no. So far we have set up our cameras. We've taken 3 camera views of the dancer performing a dance move. We've taken 3 camera views of the calibration cube. We've digitized all 3 camera views on Digi-AI. The next step is to go to the regular digitized program, where we'll transform all 3 digitized views into one complete 3D project. We say File, New Project, and we'll say Megan, second. I'll say Trial 7. We click Use APAS-AI, and we go to the control points and copy from a prior file where I've already put in the control points. We have 8 points on the calibration cube, looking good. Now we say OK. And here it asks us for the video, and we have create multiple videos. We'll say we have 3 videos, and we select the first one, and APAS-AI puts in all 3 views. OK. Now the program wants to know if there's for any reason that the digitized view is offset from the actual AVI, and we say no, it's okay as it is. Does this for all 3 views. And now we have to reopen the 3 views. These are high resolution views, so you really can't see everything at once unless you go to View, Zoom, and Cut Back. You can see that the frame number 1 is already digitized on all 3 views. Go to frame number 2, number 3, and you can see it's starting to move. Before we do that, we have to do one more step, and that's set up the So the next step is to put in the control points. We go to Control, Digitize, and open the control video. Make it smaller. And the AI program has already chosen a fixed point. You see here it's asking for the fixed point on the bottom. And here's the fixed point. I say, okay, boom, there it is. And I'm starting my A points along the back side of the X. 1, 2, 3, 4, 5, 6, 7, 8. Each of these points corresponds to an XYZ coordinate in the calibration file that we've created before. We'll then go to the next video and do the same thing. Open the video for the control. Zoom it down a bit and repeat the procedure. Fixed point. I choose the same starting point on the cube from a different perspective. Go to number 3. Open the video. Bring it down in size. And we see that it's a different camera view. Again, do the fixed point. And I have to remember that this is the starting point now from a different perspective. 1, 2, 3, 4, 5, 6, 7, 8. Now we say finished. And all 3 views are digitized. Just to ensure myself that that's true, I can say image, go to last. And we see it's image number 276. It's digitized already. So we can do that on all 3 views. When we're ready, we say DLT for transformation and filtering. In this case, we're going to use quintic spline filtering at 3 centimeters. Transforming. And file's complete. It is 3D. We can spin it around. And we can look again at the video that's been digitized. And repeat the process that we did before by asking questions about the performance and graphing it, and everything would run smoothly together. That's the conclusion of today's demonstration. We've created a project from A to Z. We've demonstrated how the completed project can be analyzed by a coach, biomechanist, physician, parent, anybody that knows a little bit about biomechanics. And we thank you for your time. And in closing, we say goodbye.